So this is our gas laws. Remember when we went through our gas laws a couple weeks ago, we learned, or at least we covered each individual gas law as we went, talking about the relationships between two variables and how they respond to each other. And then at the end, we put them together into one gas law. And so I said if you wanted, and my suggestion is to just focus on that one combined gas law. So that way you don't have to figure out, okay, which law do I need, and trying to remember all of them. Remember one, use it for all of your problems, and then you fix it and make it match your problem. So this is a problem that we're going to use that combined gas law on. So first of all, my suggestion is to write the formula. So without erasing any variables right now, what was our combined gas law? Do you remember? P1, V1 over T1. We also threw in N1 there. Equals P2, V2 over N2, T2. Remember that this equation without the n's is on your cheat sheet. And so you don't have to memorize the whole thing, but what you do need to remember is that if you need to put the n's in, they go on the bottom. If you put them on the top, you're going to get a completely wrong answer. So you need to remember that if you're going to use the n's go on the bottom. So of these variables, which ones can we erase for this problem? Pressure, right? There's no pressure involved in this problem, so I'm going to erase it. If it's not mentioned at all, you can erase it. If it specifically says it does not change, or it's a constant pressure or constant volume, that means you can erase it. So we erased our pressure. Is there anything else we can erase? N. There's no mention of moles. It's not mentioned, and also, in order for moles to change, you have to add or take something out. And it definitely does not say that's happening. So we can erase the n's. So what we're left with is volume and temperature. And if volume and temperature are definitely both in here. So here is a volume, here's a temperature, there's another volume, then our answer we're looking for is temperature. So my next suggestion is to write out one under the next what each variable is. And so what is the value of V1? 150 milliliters. What is T1? 25 degrees Celsius. What is V2? 100 milliliters. And T2 is what we're looking for. So is everybody able to look at that problem and figure out which are the ones and which are the twos? Because occasionally people have problem pulling the numbers out of the problem. They see that yes, they're volumes and temperatures, but getting at sort of the word problem part of it and figuring out what is the beginning and what is the end. So we've got V1, T1, V2, solve for T2. We can just plug them in and go, right? That's all there is to it. So I've got V, 150 divided by 25 equals 100 divided by T2. So we need to solve for T2. Is that correct? Yes. Exactly. Yes, thank you. This is something that people forget to do. I don't know how many of you forgot, how many of you just don't want to say anything, how many are still asleep from spring break or what, but you have to convert to Kelvin. If you're dealing with gases, it must be in Kelvin. And so T2 is what we're solving for. So that will work itself out, but T1 has to be in Kelvin. So do you remember how you convert from Celsius to Kelvin?
Add it to 275.
273.15. That's on your cheat sheet, but it's 273.15. So 273.1. Oh, I'll just write the first one now. 25 plus 273.15 equals 298.15. So I'm going to erase my 25 Celsius and put in this number, 298.15. Now I need to solve for T2. And so I'm going to have 2 equals 100. I also see people struggle with the algebra. Technically, algebra is a prereq for this course, and so I'm not able to devote time in class to going over how to do the algebra, but if you're struggling, please let me know or find some way to get it sorted out. Because if you're struggling with the algebra, no matter how well you understand the chemistry part, you are not going to get the right answer. Okay? And so if you're not comfortable doing this, we need to get it sorted out. So if you do this, what does this come out to be? What is it?
198.7. That's 4 feet around that.
That wasn't you that said 198. Okay, I was going to say, my head sounded like a camel from you and you didn't have a calculator. Okay. 198.7 Kelvin. Is that the end?
No.
No, why not?
You have to turn it back to Celsius.
Right. This problem in particular specifies what is the new temperature in degrees Celsius. Normally that won't be tacked on to the end, but in this case it is. And so we need to change 198.7 Kelvin into Celsius. How do we do that?
Minus 237.15.
273.
Yeah.
So to go from Celsius to Kelvin, we added 273.15. To go from Kelvin back to Celsius, we subtract that back off. Minus 273.15. What does that come out to be?
Negative 74.39.
Negative 74.39 degrees Celsius. These gas law problems lend themselves well to a double check at the end. Does it make sense? And so we went from 150 milliliters to 100 milliliters. Volume went down. If volume went down, would you expect your temperature to have gone up or down? Down. As things cool off, they shrink. Did our temperature go down? Yes, it did. And so we're not 100% sure it's correct, but we know it at least went in the right direction. And so we have a little more confidence in ourselves. If you use logic and you say it should have gone down, but your math said it went up, then you know something's wrong. So in this case, it seems to have gone in the right direction, so we're going to trust it. Yeah, go ahead.
Since at the end they ask for Celsius, if you don't change it to Kelvin in the beginning, do you get the wrong answer?
Yes, you get a very wrong answer that is not, it means absolutely nothing.
Really?
Correct. You have to convert it. When you do this, because this conversion is addition, not a multiplication, this whole thing gets thrown off if it's not in Celsius. Sorry, not in Kelvin.
I understood what you meant.
So we should change Celsius to Kelvin like right after we see, okay, we have the first temperature.
Yes, and so
First given.
I would change Celsius into Kelvin before you plug it in. I plugged it in just to see how long people are going to let me go. before I.
Also, that was wrong.
Yes. You would never, ever, ever, ever put a Celsius into a problem like this. It's not going to end well. Other questions?
So, always Kelvin no matter what?
If you were dealing with a gas, it's Kelvin.
Okay,
If it's a gas, so if it's a gas law, it's going to be in Kelvin. There are a couple other gas laws that we haven't learned yet. And so if you're dealing with gases, it's Kelvin. Where I struggle and where I'm tempted to say, if people are tempted to think, always use Kelvin. But what we did before the gas laws, the specific heat, that's Celsius. Technically, if you did it in Kelvin, you would get the same answer at the end, but the specific heat has degrees Celsius in the units. So technically, you're supposed to be Celsius. So my suggestion is, if you're dealing with gases and gas laws and things changing with gases, it's Kelvin. Hey, matches. That's always good. So here's another one. This one's Avogadro's law, but we don't have to remember what Avogadro's law is. We can just come back to our combined gas law and fix it to match our problem. I'm going to put the P's and the N's back in. Which variables can I erase here? Pressure and temperature. So in this case, we're just dealing with volume and moles. So what is V1? 8.2 liters. What's N1?
0.35 mole.
0.35 moles. What is V2? That is what we're looking for, correct? So N2 is what? 1.2 moles. Do we need to convert anything? We have moles for N. V1 is liters. Is liters okay? Yes. For volume, you can use essentially any unit you want as long as they are both the same. In this case, because we only have one, what that means is whatever unit we put in here will get out here. We're putting in liters, so our answer will be in liters. If we put in milliliters, we'd get milliliters. If we put in gallons, we'd get gallons. In this case, everything is okay. All we have to do is plug everything in. So we have 8.2 divided by 0.35 equals V2 divided by 1.2. So V2 equals 8.2 times 1.2 divided by 0.35. What does that come out to be? 28.1. 28.1 liters. Don't forget your units. It's liters because we put liters in for V1. Before we check it, let's see, does it make sense? Which direction did our number of moles go? Up or down? Up. If you put more gas into a balloon, would you expect the volume of the balloon to go up or down? Up. Did it go up? Yes. We went from 8.2 liters to 28.1 liters. So it seems to have gone in the right direction, so let's trust what we did. And we're correct. So here is another one. So this is a problem designed specifically for the combined gas law, but we're not going to do anything different other than, in this case, I think we only get to erase one variable. So which variable are we going to erase for this problem?
You're in.
on N. Moles are nowhere to be found. We have volume, we have temperature, and we have pressure. And so those all have to stay. What is P1? 2.75 atmospheres. V1 is 1.25 liters. T1 is 80 Celsius. P2 is 5 atmospheres. V2 is unknown. T2 is 185 degrees Celsius. Which of these variables do we have to convert before we can do our problem?
Celsius to Kelvin.
Celsius to Kelvin. Both temperatures are in Celsius, so we're going to have to convert those to Kelvin. Are my pressures okay in atmospheres?
Yeah.
Yes. Pressure, like volume, as long as they're both the same, you're fine. They can be atmospheres, they can be torr, they can be millimeters of mercury. Those are the three that we're going to use. But if you had something like PSI, that would also work here. So pressure's okay. Is my volume okay? Yes. It's liters. All that means is when we solve for V2, it will also be liters. So I'm going to take my T1 plus 273.15, which is my actual T1 to Kelvin. 352.15?
353.
Of course, there's no reason for it to be Kelvin. What is this one in Kelvin? 458.15 Kelvin.
What's in a smiley face?
Where?
The Celsius equals.
That, oh. So now all I have to do is plug it in. So I'm going to do this over here. Okay, 2.75 times 1.25 divided by 350.15 equals 5 times 2 divided by 8.15. That makes V2 2.75 times 1.25 times 8.15. When you do all that math, what does that one come out?
I got 0.892 liters.
0.892 liters. Okay. So, first of all, what direction did our volume go? It went down. So let's see if that makes sense. In this case, because there are two variables that changed, in some cases you're not going to be able to figure out which way do you think it went. Okay? It depends on whether they went in opposite directions and had opposite effects on the volume, or if they both had the same effect on volume. So let's first look at our temperature. Our temperature went up, right? And so if temperature went up, would you expect our volume to go up or down? Up. And so based on the temperature change, we would expect our volume to have gone up, but it went down. So at first check, it's not looking all that promising. But let's look at the pressure. Our pressure went up, went from 2.75 to 5. If pressure goes up, which way would you expect your volume to go?
They're opposite. So it goes
They're
down.
opposite, and so it would go down. And so in this case, the temperature is trying to make the volume go up, the pressure is trying to make the volume go down. And so unless you really dig into each one and how much they went up and down, it's kind of a draw, and you don't necessarily know which way your volume is going to actually go. And so, because we can't immediately tell, well, we know it's going to go up, we know it's going to go down, we trust ourselves. And so we're going to say that that is the correct answer. And it is. So, if you had a combined gas law problem that also had moles in it, it doesn't get harder, it just, you can add more numbers. And so it gets a little trickier in terms of algebra and keeping everything in place. But the problem itself does not get any harder. You just have to use all 4 variables. Before we move on, any questions about any of these? You're going to do quite a few of them. On homework, on quizzes, on exams, and lab. Okay. So, we had Boyle's law. We had Charles' law, Avogadro's law. We took those 3, turned them into our combined gas law. And if you do a little bit of math magic, you can turn this into something that looks like this. PV divided by NT is always constant. And that's why this is true. If P1 V1 equals N over N1 T1 equals P2 V2 over N2 T2, that's because this is always equal to a specific number. And because that is always equal to it, that will also be equal to it. And so if they're both equal to the same number, then they're equal to each other. And so 3, 4, 5, 6, 7, they would all always be equal to each other. And so once you figure that out with algebra, you go to the lab and you say, well, what is that number? And somebody did that a long time ago and came up with the ideal gas law. This is another gas law. I believe this is on the cheat sheet.
Yeah, it is.
Is it? So this is PV equals nRT. This is the ideal gas law. At the bottom again, I've rearranged it for you, but the only one on the cheat sheet is that one. So in this equation, we still have pressure, volume, moles, and temperature, but we now have this R. That R is that constant number. And so if we go back, PV divided by NT equals R. And then if you move these over to that side, multiply both sides by NT, you end up getting that equation. So here is that R divided equals PV divided by NT. If you go in the lab, you figure something out, put them in, what you figure out is that R is equal to 0.08206 liter atmospheres per mole Kelvin. That's not a unit you're ever going to have to just pull out of midair. The value of R is on the cheat sheet. I will warn you, though, that there are multiple values of R, depending on which units you use. If you use atmospheres instead of torr, this number is going to be very different. And so the one that you want is the first one. So the very first thing on your cheat sheet is Avogadro's number. The second thing is the value of R. There are 3 values of R. You want the first one. And the cheat sheet, and every scientist who has ever actually been a scientist rounds this to 0.0821. I don't need you to do 0.08206. 0.0821 is fine by me. That's what's on here. And so right there it says 0.0821 liter atmospheres divided by mole Kelvin. And so the unit is right there for you. Okay. Where that comes from is liter atmosphere mole Kelvin. You just take the units from the math and stick them there on the values of R. So this is an example of an ideal gas law problem. When you get a gas law problem on a quiz or an exam, the first thing I want you to do, before you look at numbers or anything like that, read the problem and figure out, is anything changing, or is the problem one point in time? The combined gas law, this is for when things are changing. Remember, there's always volumes changing. What does that make the new pressure? Temperature is changing. What does that make the new volume? Something like that. In an ideal gas law problem, nothing is changing. It is one point in time, and you're missing one variable. So I want to look at that problem and think about how that problem is different than the other ones we've seen. Make sure you can see that this problem is dealing with one point in time. So we have a 6-liter container. It's at a pressure of 700 torr, a temperature of 25 degrees Celsius. What mass of oxygen is in that tank? It's a tank, it's sitting here, nothing is changing. We have to figure out how much oxygen is in that tank. So in this case, because nothing is changing, we have PV equals nRT. What is my value of P? 700 torr. What is my value of V? 6 liters. What is N? We don't know. R is off your cheat sheet, 0.0821 liter atmospheres mole Kelvin. And then we've got T. T is 25 degrees Celsius. Now we have to figure out which ones we need to convert. In an ideal gas law problem, the volume has to be liters. And you know that because the value of R has liters in the unit. The unit on R is going to tell you exactly what units your volume, pressure, and temperature need to be. If any of them are not those units, something is wrong. So we need to convert everything into these units. So my volume is already in liters. So that's fine. Pressure is in torr. We need to convert pressure from torr to atmospheres. Do you remember how to do that?
760.
760, yes. It's on your cheat sheet. 1 atmosphere equals 760 torr. And so, what's 700 divided by 760? 0.92. 0.92? Thank you. 92 atmospheres. RT has to be in Kelvin. It's gases, it's a different gas law, but it's still gases. And so we want Kelvin.
298.
Thank you. Kelvin. Now we have the right units. So we can plug it in. So we've got 0.92 times 6 equals N times 0.0821 times 298.15. So N equals 0.92 times 6 divided by 0.0821 times 298.15 equals what?
0.2258 moles.
0.226 moles. Is that the final answer?
Yes. Yes.
Change it to grams.
No, it's in moles.
It says mass is in grams.
Correct.
Oh.
This problem says what mass of oxygen gas will occupy the container. And so what we solved for was moles. We couldn't solve for grams because N is moles. And so now that we've solved for moles, we have to convert moles into grams. And so we have 0.226 moles of what? Oxygen, which, how do I write that?
O2.
O2. Oxygen gas is O2, is diatomic. It's like hydrogen or nitrogen, or chlorine, bromine, anything like that. Remember the diatomic elements. So 1 mole of O2 weighs how much? 32. Each oxygen is 16. There's 2 of them, so we have 32. So what is my mass?
29.47.
29.47 grams of oxygen.
Yeah, I got
Yeah, I got
7.2.
7.2.
Yeah, and I can see it. That doesn't make, that's going to be much less than that. Yeah.
Someone did that math.
Try your calculator again. So something's off.
You probably put 2.26.
Yeah.
Is that what you did? Okay. Nice. Here's another one. We have an oxygen tank. And the oxygen tank is a little over 2 liters in size. When it's empty, when you have a tank of gas, it's empty. It's not actually empty. If it was empty, there'd be a vacuum in there, and the universe would collapse on itself. It's not going to happen. So there's always something left in there. It's just there's not enough in there to be useful. So in this case, we're going to figure out how much oxygen is in that tank when it is empty. And so we're going to say it's essentially it's a warm room temperature, 29.2 Celsius, and the pressure gauge on the tank says 723 torr. We have to figure out how many moles of oxygen gas are left in that tank. So this one, it's asking it in moles, and so we don't need to do that conversion at the end, which will save us a little bit of work. So we have PV equals nRT. Again, N is what we're looking for. So pressure is what? 723 torr. Volume is 2.025 liters. N is unknown. R is 0.0821 liter mole Kelvin. Temperature is 29.2 degrees Celsius. Which ones do we need to convert?
Pressure and temperature.
Pressure and temperature. We need liters, atmospheres, we're in torr, so we have to convert that. Moles, that just means we'll get moles out. And Kelvin, we need to convert temperature to Kelvin. So let's convert that to atmospheres. Divide by 760.
1964.
964 atmospheres. Temperature,
302.2.
302.35. Did you add the 0.15?
No.
Okay. Kelvin. Now we can plug them in. So we've got 0.964 times 2.025 equals N times 0.0821 times 302.35. and 0.964 times 2.05. What does that equal? .08 moles of oxygen. Does everybody get the same number? I'll take silence as a yes.
The pressure problem.
Pressure.
Yeah, I got
That's what I got.
0.95.
I have one.
Probably no.
9.5.
Yeah, that's like
Okay.
0.5. Changes the whole problem.
Just a tiny bit. You'd be so close that I would probably just mark it correct. Remember, there's always laziness on the professor's point also. If you're so close, you can just say, well, I'll mark it correct and I don't have to figure out what they did wrong.
That's not something you say.
So what does that come out to be now?
One makes up close to
0.77.
So technically, if you round it, it'll
Yeah,
still be 8.
that's what I mean. It's so close that
Okay.
It's right.
it's so close that it's right.
But you were wrong.
So how many sig figs? So technically, we had 3 sig figs, and so it would be that. Okay. Is everybody okay with ideal gas law? In my experience, people are okay doing this. People are okay doing that. What they struggle with is knowing which one to use. So make sure you look at a problem before you do it and ask yourself, is anything changing or is it one point in time? That's really the hardest part. That's the only part that really requires thought and logic. Figure out which equation you need. At this point, we only have 2. I've gotten rid of all the Boyle's and the Charles and Avogadro's laws. You don't have to worry about it. They're all contained in here. The last law we have to talk about is Dalton's law. What this law says is that if you have a container and it contains multiple gases, multiple different gases, the total pressure in that container will just be the pressure of each gas added together. And so you can essentially think of each gas in that container acting totally independently. So if we fill a tank with air, we know that there's going to be a lot of different gases in that tank, right? Mostly nitrogen, quite a bit of oxygen, some hydrogen, things like that, right? So the oxygen, there's a certain number of moles of oxygen in that tank. You can use the ideal gas law to figure out how much pressure that many moles of oxygen are going to make. Do the same thing for the nitrogen, and the hydrogen, and the helium, and the argon, and everything. And if you just add them up, you're going to get the total pressure in that tank. If you put a pressure valve or a gauge on that tank, it's going to tell you the total pressure. A pressure gauge cannot tell you the pressure of just the oxygen or the nitrogen. It can't tell the difference between them. Stupid pressure. Yes. And so there are a couple ways you can look at this problem. Number one, you can say, I know the pressure of gas A, the pressure of gas B, the pressure of gas C, I can find the total pressure just by adding them together. You can also work the other way, though. If you know the total pressure, and you know the pressure of A, and you know that the only other thing in there is B, you can find the pressure of B. and if you know the pressure of B, you also know the volume of the tank, and you know the temperature, you can solve for the moles of B also. Yeah. So the type of problem you're going to see that deals with Dalton's law, other than something very simple, just add them together and you get that, is a problem that makes you realize that whatever fraction of moles of gas are a certain element, it's going to give that same fraction of the total pressure. I realize that probably made no sense. It was kind of foggy in my head as I was saying it. But what that really means is that if you have two gases in a container, let's say oxygen and nitrogen, if what is in there in terms of moles is 1/3 oxygen and 2/3 nitrogen, the oxygen is going to contribute 1/3 of the pressure, and the nitrogen is going to contribute 2/3 of the pressure. 1/3 of the mole gives 1/3 of the pressure. 2/3 of moles gives 2/3 of pressure. So let's see an example of that. Let's say we have a tank, and that tank has a total pressure of 10 atmospheres. I know that in that tank there are 3 moles of oxygen and 7 moles of nitrogen. I need to find the partial pressure, meaning what is the pressure of the oxygen and the pressure of the nitrogen. We say partial pressure of oxygen, partial pressure of nitrogen, because they're a part of the total pressure. So how are we going to find the pressure of the oxygen and the pressure of the nitrogen? The only information we have that's specific for each element is the moles, right? The only pressure we have is some generic total number. And so that's not a good place to start. We're going to have to do something with these moles and then apply it to our 10.
Add them together and find the total numbers and find the fractions of each.
Exactly, yes. So how many total moles do we have? 10. Oh look, the math came out convenient. There's 10 moles
Usually
total.
examples are easy. The problems that are in homeworks and tests
I know, right?
quizzes aren't easy.
This one, this problem on the homework in the quizzes will be.
How about the test?
Yeah.
Okay, alright, that's important.
So we have 10 moles total. Of that 10 moles, 3 are oxygen.
Trace.
So there's 3/10 of the moles come from the oxygen. And so 3/10 of 10 equals 3 atmospheres from the oxygen. The nitrogen is 7/10 of the moles, so 7/10 of the pressure is going to be 7 atmospheres
Under pressure.
from the nitrogen. Okay, so you want a more complicated one?
No.
Yes. Okay. So we can do this with any number, I believe. We'll see if it works. I think we can use any number.
I don't have a calculator. I can't figure the other ones out.
So give me a number between 1 and 100 with no more than 2 decimals.
6.
Just 6? 6.2 atmospheres. This works with atmospheres, with torr, which with anything you want. What's your favorite gas?
Oxygen.
What's your second favorite gas? Don't say
Carbon
nitrogen.
dioxide.
I was just about to say.
Can't say nitrogen. What's your third?
Helium.
No.
Xenon?
Oh, don't say
What was the other one?
Helium.
Helium. I thought somebody said chloroform. We'll go with xenon.
Right? That's funny.
So in this case, we have 3.
What's the elements for chloroform?
It's CCl4, carbon tetrachloride. I think it's either CCl4 or CHCl3. I think it's CCl4 though. Give me a number between 1 and 100 with 2 decimal places for oxygen.
23.82.
23.82. Give me another one.
1.
1.11.
1.
And xenon 0.75. Okay. So we now have to find the pressures for each gas. So first of all, we have to find the total number of these are all moles.
Those are a lot of moles.
That's a lot of moles.
You should call exterminator.
So what's the total number of moles that we have? It's 25 point something.
6.8.
25.68 total moles. So we do oxygen first. So I've got 23.82 divided by 25.68. That's going to tell me what portion of my total moles is oxygen. So that'll come out to be a number. It'll be a little less than 1. And then I multiply that by my total pressure. So what is my pressure from my oxygen? It makes sense. I mean, almost all of our moles are oxygen, and so almost all of our pressure should be oxygen, which it is. Do the same thing for CO2. In this case, we've got 1.11 divided by 25.68 times 6.2.
.2679.
26 atmospheres of CO2, and then we do xenon 0.75 divided by 25.68 and 6.2.
0.181.
0.181 atmospheres. So we literally picked random numbers. And so that's about as hard as I can get. The problem itself wasn't more difficult, it's just you had to use your calculator for the math. That make sense?
How would the question be worded for this problem?
It would be similar to this, but it would just be in sentence form. Yeah.
So we would just add those pressures and that's our answer?
These individual pressures
The
are
individuals,
here,
yes.
because these added together better equal 6.2.
Okay.
If they don't, then something's wrong. Okay. So I think the last thing we've talked about for our gases is what's called the kinetic molecular theory. We've already talked about kinetic molecular theory without actually talking about kinetic molecular theory. When we learned about the basic ideas of the gas law, what causes pressure, why temperature changes cause change in pressure and volume, we talked about what was happening at the molecular level. That essentially is the kinetic molecular theory. And so here at the end, we're going to put them together into these 5 specific definition of the theory that we call postulates. The first one just says that gases are made up of particles that are very small and far apart. They're widely separated. This explains why in a gas, almost all of it is empty space. Because the particles are very small. If you have this much gas, just a tiny bit of it is actual atoms. The rest of it is empty space. It also explains the low density of gas. Because empty space weighs nothing. Remember, density is mass divided by volume. Empty space has a lot of volume, but no mass. And so you have a very small m, a very large v, and so your density is very, very small. Also explains why you can compress a gas. All that empty space is just waiting to be taken up. So if you compress it, the molecules just come closer together. Now you have less empty space. If you didn't have any empty space, like in a solid or a liquid, you can't compress it very well. Second postulate says that each particle behaves independently of one another. So they fly around on their own until they hit each other. And when they hit each other, they bounce off. There's also no attraction or repulsion between the gas particles. And so they're flying in straight lines. When they hit each other, they're going to bounce. It's not like a space shuttle, not space shuttle, I guess an Apollo lander or whatever, going around the moon, where there's a force, where it comes close to it, doesn't actually touch it, but there's a traction between them that causes a change in the movement of the small particle. Okay? So they fly in straight lines, they hit each other, and bounce off. And that's postulate 3. When they hit each other, then they bounce off each other. And we say that those collisions are perfectly elastic. That's a physics term. What that means is that no energy is lost when they hit each other. Elastic is springy, right? When imagine two bouncy balls hitting each other. They just bounce off. They don't really lose any speed, right? They just bounce off each other and go. But if you have two balls of wet clay and they hit each other, what's going to happen? They're going to smush together, and even if they bounce off each other, they're going to really slow down when they do it. That's called an inelastic collision. Okay, so gas molecules, when they hit each other, that's perfectly elastic. And that's a good thing. Because think about it. If every time a gas molecule hit another gas molecule, we lost energy, what do you think would happen to the energy in the universe?
We wouldn't have it.
We wouldn't have any, right? Because the gas molecules are constantly bouncing around in here. If every time they hit each other, I mean, there are, think about it, for every mole of gas, there are 6.022 times 10 to the 23rd atoms or molecules. Think of how many moles of gas are in this room and how many billion, quadrillion, zillion molecules that is. If every time they hit each other, they lost energy, it would go from room temperature to absolute zero faster than you can say femtosecond. Okay? So this is why everything is allowed to happen in the universe. Fourth postulate says, like we talked about earlier, the pressure in the container comes from the collisions of this particle inside the container with the outside. So if you have a bunch of particles inside, they're going to hit the container more often. And so the pressure is going to be larger. If you put more gas in, pressure goes up. If you raise the temperature, you're not going to have more particles, but they'll be flying faster. And so when they hit the wall, they're going to hit it harder. So the same number of particles will be able to give you a larger pressure. If you decrease the volume of the container, now the same number of particles are in a smaller container. They're going to hit the wall more often. If they hit the wall more often, pressure is going to go up. And number 5 says the average kinetic energy of the gas particles, the molecules, the atoms, depends only on temperature. So we talked about kinetic energy at the beginning of last week's lecture. What was kinetic energy? Energy of motion. And so the more kinetic energy you have, the faster you're moving. And so what this says is the only way to change how fast that particle is moving is to change the temperature. If you heat it up, it'll move faster. If you cool it down, it will move slower. Okay. We have one last slide here. This looks like an innocuous slide that's not important. That is not the case. This is an important slide. I want you to circle it. I want you to highlight it. I want you to go over this before the quiz next week, before the next exam, and before the final exam. Okay? This is an important slide. All of these gas laws that we went over assume the gas that we're dealing with is an ideal gas. Think about it. When we did each of those problems, it didn't matter what the gas was. It didn't matter whether it was oxygen or nitrogen or carbon dioxide or xenon or methane or anything you want it to be. We didn't even take that into consideration. We assumed that all of those gases were going to act like this so-called ideal gas. We said earlier that the ideal gas gives these very nice proportions. As volume gets cut in half, pressure doubles. If you divide the volume by 2, pressure gets multiplied by 2. That is an ideal gas. In real life conditions, gases are so close to an ideal gas that we can't tell the difference. But in some situations, they are not. A collision between molecules is not completely elastic. In fact, when molecules hit each other, they lose the tiniest amount of energy. But it is so small that in our lifetimes, it's not significant. In the lifetime of the universe, it is significant, though. And actually, attractions do exist between molecules and atoms in the gas phase. But luckily, because they're so far apart, they spend very little time next to each other. And so if the two atoms are out here, those attractive and repulsive forces are negligible. They're basically non-existent. They only exist when they're right next to each other, which is only a very small portion of the time. But if you get a very high pressure, meaning you have a lot of atoms very close to each other, either you decrease the volume or you put a whole bunch of gas in there, now there's a lot more atoms in a small space. They're next to each other a lot more often, and so those attractive forces are occurring a lot more often. So that, in that case, that can happen. Same thing with very low temperature. If you have a very low temperature, gases come in, the volume is going to decrease. And so the atoms are closer together, and so these attractive forces will start to have some effect. But this high pressure is extremely high. This low temperature has to be extremely low. It's not something that we can accomplish in lab. We're talking like theoretical physics type stuff. But just keep in mind that gases aren't actually ideal. That's something that we made up to allow us to make these nice equations. Okay, that's the end of gases. Any questions on gases? Okay. We're a little early for break, but it's such a neat, nice place for a break. Let's take our break now. We'll start at 1/4 after on that clock.